Very good afternoon, everyone. So today we are going to have a demonstration session on SEM and XRD. These are two core facilities required by people working on any kind of materials. And for today's demonstration, Bidyendu is going to help us. So Shri Bidyendu Roy did his BSc from Ramakrishna Mission Vivekanand College and his MSc in Physics from APC College. He further pursued his B.Ed from Kurukshetra University and also taught as lecturer in Saroj Mohan Institute of Technology and RKMVC College. He was technical assistant at Heritage Institute of Technology till October 2016, after which he joined us at IIT Patna. So, Bidyendu, yeah, so I think you
Yes.
belong to Chakda in West Bengal, right?
No,
Okay,
sir,
so
that was
Bidyendu,
the.
please proceed. Yeah,
Okay.
hello? Yeah,
So, okay, sir. Sure. Am I
yeah.
audible?
Yes, you are audible.
Okay. Okay. Thank you, sir. So, welcome to FESEM and XRD lab. So, this is the FESEM machine, and so this is the FESEM machine. So, I'm going to demonstrate this FESEM, and after that, I'm going to demonstrate XRD machine, which is situated in the same lab, and then we'll show how the data is analyzed. So uh, first start with this machine. So FESA machine. So this is SEM, that is scanning electron microscope. So yesterday TEM, that is transmission electron microscope, was demonstrated, and it is also of same kind, but the operations and the are different. Same kind means it is also an electron microscope. But in the TEM, the transmission of electrons happens through the samples. And here, SEM means scanning electron microscope. That is, it scans in the surface level of the sample. So it doesn't penetrate the whole sample, and it doesn't transmit the electrons which are originated, which are basically primary beam. That doesn't penetrate the whole sample, unlike TEM. So like these machines, we have also the same types of things, like electron gun is required here to generate the electrons. Then we require the lenses, condenser lenses, as well as the objective lenses, like in the TEM, and then samples specimen chamber, then specimen exchange chamber. So these parts are more or less same, and the detectors are also same for X-rays, to detect X-rays. So I'll demonstrate one by one. So first here, the electrons guns are situated where the electrons, the primary electron are generated, and some anodes are there, and and we apply a high voltage to the cathode and anode. So the electrons which is generated from the tip. So here we use a tungsten tip. So that is why it is called field emission electron scanning electron microscope, FESM. So another type of source can be used in that is in the thermoionic source. So here we use a tip of tungsten. So that is why it is called FESM, field emission scanning electron microscope. So from cathode and anode, there is a high voltage we are applying, so that the generated electrons are accelerated downward, okay, in the scattered orientations. So to focus that things, we need some lenses. So that lenses are not the physical lenses like in the optical microscope. So electromagnets are used, and we control the magnetic field to actually to direct the beam. So a thin diameter beam is required. That is called the primary beam. So through condenser lenses, here it is first condenser lenses, and then second condenser lenses is situated. So it is the aperture for the condenser lenses. Like we have seen already CL, which has been inserted manually, but it is actually fixed. Like unlike in the TEM, it has to be inserted, but it is already inserted, and it is fixed actually. So we don't have to insert it manually. Then we have second condenser lenses. So through these condenser lenses, the primary beams are basically is directed downward like a beam, like a thin beam, and it passes through the objective lenses. So objective lens is situated here, just above the sample chamber. So the objective lenses contains the scanning probes, scanning coils rather, so which is responsible for the scanning of the morphology, that is of the surface of the samples. So we can have the we can see this image. So is it visible? The image is visible. Schematic diagram or sectional view.
Yes, it is visible, Bidyendu. Yeah.
Okay. Okay, sir. Yeah. So in the core part of this instrument, it is the sectional view of this same model, that is S4800 Hitachi FESEM. So here the electrons gun is situated. Here is the electron gun is situated. Then it comes through this cap, and then the primary beam which is originated, that is accelerated if we apply high voltage here, and then it is directed in the downward as per the Lorentz force. So Lorentz force is acting in this model or in this microscopes. So the beam which is through this first condenser lens and this second condenser lens, it is actually focused, and then it falls to the objective lenses. So here the objective lenses are situated, and then the objective lenses, the coils, the scanning coils of the objective lenses that scans the sample which is situated just below the objective lenses here. So here is the specimen chamber, or shortly it is called SC. And through this, we exchange the samples or specimen. So this is called the SEC, that is specimen exchange chamber. Okay. So how it scans? It has the periodicity. Like it starts from whenever whatever we have chosen the area, we have to choose through the softwares, and then it just through these coils, it just scans in a periodic way, in a line by line. So suppose it starts from here. Suppose it is the sample or specimen. So it starts from here, and then it scans in a line, then come back, then again it scans. Likewise, it will cover the whole area which is been exposed to the electron beams. And after getting when the electron beam, primary electron beam, it interacts with the samples. So different types of secondary electrons or auger electrons, different types of electrons or X-rays are generated through the surface of the samples. So depending on the penetration in the surface level only, not to the depth of the sample. So it just depending on that depth of the penetration in the surface, different types of electrons are generating. Like in the upper part, some 1 or 2 nanometer, if it penetrates, then auger electrons will be generated. Then if it penetrates up to 10, suppose 10 nanometer distance in the surface only, not in the core. So it will generate secondary electrons, and further it will generate further if it penetrates up to some micrometer, 1 or 2 micrometer, then backscatter electrons are generated. And when it penetrates like a 5 micrometer or something, so that will generate the X-rays. So for generating the X-rays, we have to apply more voltages. So it is operating up to 30 kV, 30 kilovolt voltage. So just for secondary electrons, generating secondary electrons or backscatter electrons, up to 15 kV is enough. So from 1 to 2 kV to 15 kV, we can do the scanning, just morphological scanning. But to generate the X-rays, and to study the excess, we need further voltage that is above 15 kilovolt. So the electrons which in or excess which are generated after interacting with the samples that will detect by these detectors. So we have this secondary electron detector, and here another secondary electron detectors are there. So two secondary electron detectors are there. One is at the bottom level and one is at the upper level. Then the backscatter electron detectors is actually situated in the annular region of the primary beams itself. So it doesn't actually the primary beam, suppose it is falling like this. So the backscatter electron detectors are situated like in the annular form of the hair. Okay, then we have this X-ray detectors, which is of the make Oriba. So through these, the X-rays are detected, and we use different monitors. So there are two monitors here. So one is for the morphological analysis, that is through the secondary electron detectors, and for X-ray detectors we use this monitor. So for auger electrons in FEM, we don't have any detector, or for the auger electron is not responsible for SEM here. So the secondary electron detector is responsible for the morphological analysis. And the whole column should be in the vacuum. Otherwise, when there will be air molecules, so the beams which has been generated, the beams will not be focused on the sample. So it will be diverted by, and besides that, it will actually ionize the air, and it will lose all the energies in ionizing them, and the contamination will be occurred in the tip of the filament. The tip of the tungsten tip in the source. Okay, so the vacuum systems which are available here is ion pump 1. It is situated here. Then ion pump 2 and ion pump 3. So 3 ion pumps are there. Then we have a TMP. We have a TMP and buffer tank, and also a rotary pump which is situated in the back side of the machine. The back side of the machine. Okay. So the values of the vacuum level we can see from here to this mode. So ion pump 1, it is blinking, that is the value of the order of 10 to the power minus 8. IP2, it is also of the order of 10 to the power minus 8. And IP3, that is also 10 to the power minus 8 in the order of. But in SC, that is the sample chamber where the sample is kept for scanning, that value is of the order of 10 to the power minus 3. And it is SEC. So that is sample exchange chamber. So this panel actually it is fixed. We don't change through this. After installation, we don't touch these things. So it will be fixed, and this apertures also will be fixed. So this is the sample exchange chamber. So 4 buttons are there. One is for open and one is for close. So in between the sample exchange chamber and sample chamber, a shutter is there. I think you can see through this. A shutter is there. So if it is in close, the shutter is closed, and if we press the button open, so shutter will be open. But we have to make sure that when we open the shutter, it must be evacuated. It must be in evacuated status, so that the air doesn't get into the main chamber or main column. So it is in AVAC, so we can open the shutter. So a sound will be there. So it is open. And by this rod, we just fix it the sample is fixed in the sample holder. Okay, then we push it up to that, and we lock it in the sample chamber. And again, after unlocking, we remove the rod. And at that time, the sample remains in that position. And we have to make sure that when we exchange the sample, so a sample exchange mode is on through the software. Okay, so I think you have seen it is visible. No? Okay. Yeah. So I'm closing the shutter. And when the shutter is closed, now we can pour it through air. So a sound will be. So you can see this is the sample stage. This is the sample stage which I've already fixed at that position. And and here is the screws through which it is locked in the sample chamber. Now I'm closing this. And again, I'll make it evacuated. And there is a chiller associated with this machine. So for cooling down the when it is in use, the objective lens is getting heated, and for that we need cooling. So we have a small chiller here. We have a small chiller here. So this is the main unit, and this is the display unit. So we are switching the display. And we have to remember that the sample should be conducting. So if a non-conducting sample is used, then we have to coat a very thin level of gold through this. So here it is iron spatter. So we use this iron spatter to coat gold up to a very thin level, just in the surface of the samples. Okay, so we generally we do for 30 seconds. So for that, For that, we have to remove this. And the sample is placed here. Not the single sample, the sample stage rather. The sample stage is placed here, and gold is here, and then we switched on. So when the vacuum level is below 10, we choose the time through this. So 20 seconds is set. So we can choose 30 and set. So when the vacuum level is below 10, then we just discharge it. And a very thin coating will happen in the surface of the samples. Then we can use the samples in the for scanning. So we are switching off. So currently this machine and as well as the XRD machine is inoperative. So due to some reasons, so you can see what is the reason here. And we're working on it, and hopefully it will be operative very soon. So the distance between the objective lens and the sample stage, that is called working distance. So we have to make sure that the sample stage is well below the objective lens. For that, this is the measurement. So we place the sample stage here, and we make sure that it is below that level. It is below that level. So here the problem is for this instrument is that the working distance is automatically getting low. So from 8, it was fixed at 0.8 at 8 mm. So it is automatically getting closer, and corresponding magnification is become higher. So quickly you can see through this. So we switch on the high voltage through this, and we choose the high voltage here, and it is auto brightness, auto focus. It is for alignment, and we choose the exchange for exchanging the samples. Okay. So, and one more thing, you observe that please flash, it is showing. So for the time being, we are closing it because it will be very closer to objective lens now. So what is the flashing? Actually, the tip, the tungsten tip is contaminated through these molecules, air molecules. So though it is in vacuum, absolute vacuum cannot be possible. So some air molecules will always be absorbed in the tip. So for removing this, the flashing is required. So if certain voltage is used to remove that things from the tip, so that process is called flashing. So we do through flashing through this software only. So here is the image of a SEM. it was done earlier. So you can see the particles here through this image, and some information is mentioned here. So here first S4800, the model name is there, and then 15.0 kV, that is at that time 15 kV volt was applied, and then it is cross 5.00 K, that is the magnification for this image was 5K, and secondary electron is used, and here is a scale is there. So from the beginning to the last, that length is 10 micrometer. So here 10 divisions are there. So one division means 1 micrometer. So we can have a rough idea. So this is the length corresponding to the value 1 micrometer. So we can through images software we can do the analysis and estimate the particle size, average particle size. So we'll do that in the later after demonstrating XRD. So after demonstrating XRD, so we'll show the analysis part of the ACM and the XRD also. So any question?
Are there questions? Bidyendu, you may
Hello, sir. Hello, sir.
so what I'm saying is you may continue. I think they're not asking any questions right now.
Okay, okay, sir. So this is demonstration for FESEM. So I'm going to demonstrate the XRD now. So this is the XRD X-ray diffractometer. So the model is TTRAX3 and the make is Rigaku. So X-ray diffractometer Rigaku. Okay. So there is a button. There are some buttons there. So first the door button. So whenever we are we require to open the door, we have to press that door button. So at the time of the door, we press the door, the shutter is closed in the X-rays where the X-rays is generated. Then the parts of this XRD is first the source. So it is the X-ray source. It is the X-ray source, and here it is the copper target. So the anode is the copper, and cathode is situated here, and with the X-rays, the electrons actually, it is the target. Okay, and the electrons are colliding with this target, and the generated X-rays are coming through this. So the first thing, it is a CBO, that is cross beam optics. So it is basically a geometry, and then it is the selection slit. It is the selection slit. We put the slits here, and then some solar slits are there, and height adjustment slits are there. So it is basically the geometry. So the X-rays which is being generated, the X-rays which is generated, it is coming through this, and we require a different types of orientations for different modes. So here we have two modes. One is for the powder sample and pellet. So that geometry is called, that is Bragg Brentano geometry, and another geometry we use for the thin films. So for that geometry is required. So the CBO, that is cross beam optics, it is actually getting switched. When we use BB, at that time the geometry will be different. There some divergent X-rays will be required. And for PB, that is parallel beam geometry, a multi-layer mirror is used, and through this selection slit, it is actually switched between the BB mode to PB mode or PB mode to BB mode. So I am repeating, for powder samples or pellet, we use BB mode. It is in BB mode orientation, and one different types of modes. It is for that we require PB mode to analyze the thin films. For that, some solar slits mean it just limits the divergence, angular divergence, and height adjustment. That height adjustment slit, it is used to limit the longitudinal width of the X-rays. Then after going through this, so through these slits, the X-rays are exposed in the sample holder stage. So it is the sample stage, and here it is the sample holder for doing the powder samples. So we place the powder here. And then we use the slides, and we have to make sure that the surface of the powder should be flat. So we place it through the slides, and then we place it in the stage. So the X-rays are now incident here. So the X-rays are incident here, and then it goes to the detector part after reflecting, or we can say that after scattering. So here also some slits are there. So you can see some again here a solar slit 5° is mentioned here. Solar slit 5° you can see. So that means it is the diverging limiting slit, and it limits up to 5° of annular X-ray. And here you can see it is a filter. So we just require only K alpha for our data. So we have to remove the K beta bar. So for that a nickel filter is used. So this is the nickel filter. And here are some aluminum absorber, because the incident X-rays, actually the magnitude is very high, the amplitude is very high. So that will damage the detector. So for that we reduce it through this absorber. So this is the detector part. So this will detect the scattered X-rays, and then through the software we get the data. And here the system which is responsible for the rotation, it is called the gonimeter. So through gonimeter, actually the source and the detector both are moving. So I'm closing the door. So the incident X-rays, it is coming to the samples and then get refracted. So the glancing angle is theta, and the angle between the reflected and the incident ray, that is 2 theta. So we just vary the 2 theta value, and we measure the amplitude, rather intensity. So first thing we have to do for switching on these machines. So it is the vacuum that is always on. Other than that, we have to switch on for. So first, what we'll do, first we'll switch on the chiller. So you can see the chiller, which is situated in the back side of this room. So it is outside the room. So that is the chiller, and water is placed there. And we switch on the chiller, then we can see. So maybe it is not, it will not be seen. So it is showing some temperature and the value of the pressure. And here it is the water in. So through this, the water is coming in the main XRD machine. So it is actually when the target is getting heated. So a high voltage is applied. So the target is getting heated. For that, we have to cool it. So we have to cool it whenever the machine is in use. So through this, the water is actually in the machine, and here is the water out. So through this, after cooling, that water will be coming through this. So the water will thus be circulated. And here is the pump that is responsible for the vacuum in the discharge tube. So here the vacuum is on, and the voltage and the current, we just increase it in a steps. So the operating voltage and operating current is generally 50 kilovolt and 100 milliampere for 5 kilowatt usage, and we can also do it for 18 kilowatt. So this machine is up to 18 kilowatt we can do. So generally 5 kilowatt is used, and for that the voltage would be 50 kilovolt and the current would be 100 milliampere. And the value of the vacuum, actually it is showing through the iron gate. So we'll be clicking XZ operation, and then from option to control, then option property, and choosing everyday. So here are some steps. So here are some steps. So first it is the 20 kilovolt and 10 milliampere. So whenever we start from the axis, the voltage will be gained to 20 kilovolt and the current will be gained to 10 milliampere. Then it will stay for 300 seconds. Then it will be automatically, it will be increased, the voltage will be increased to 25 and current will be 10. And through these steps, so from 2010, 2510, 3010, 4010, 4020, likewise 50 and 100 milliampere will gain in some 30 to 40 minutes. So the voltage we are not exposing directly, rather we are choosing a step to increase up to that to gain that voltage, required voltage. Then we're just executing edging. So execute edging means these steps will be followed to increase that voltage and current. So when it will be ready, then we'll click standard measurement, and then we'll choose a file through this browser, and then we'll give the condition. So this start angle, stop angle, that is the 2 theta. So we will increase the 2 theta value in some steps. So as per the user, we choose the start angle from which the scanning will be started, and when it will be stopped, that is selected here. Then sampling width. Sampling width means, so it is actually some 2 theta value, and it is giving the corresponding intensity. So it will start at 25. Then what will be the next point? So that is actually sampling width. So the next point here, it will be 20.02. So how? So more the closer it is, so more smooth curve we will get, right? And then the scanning speed. Scanning speed means, so here 4:10, that is 4 degree per minute. So in 1 minute, the 2 theta value will be increased to 4 degree. So generally we choose 2. Generally we choose 2. So 2 means 2 degree per minute, the 2 theta value will be increased. So after starting, so it will in a minute it will go up to 27 degree. Then we will just execute measurement. So when we click this, so measurement will start, and it will stop at that value we have already chosen, and then the data will be already automatically saved. So after that, we'll remove the samples and we'll do another sample. So after finishing the experiment, so we'll show the data just after the demonstration when we demonstrate the how to analyze the data for XRD and SEM also. So Jyotika Mullik will help us for that, and when the experiment is over, then again we'll do the reverse process. So at that time, we'll choose shutdown. Now the value will be reduced. So it will be reduced to 50 kV and 80 milliampere, from 50 kV and 100 milliampere in 30 seconds. Then it will take 60 seconds to be reduced to 50 to 60. So like this, in that steps, so the shutting down is quicker than the switching on. So in some steps, it will go to 20 kilovolt and 10 milliampere through this edging. And then we'll switch off the X-rays, and then we'll switch off the chiller. Now, is there any question regarding XRD and SEM?
Yeah, the participants are requested to ask any queries if they have.
So you can see how it is moving, how the source part and the director part is moving. So we are moving manually here. For that, we have to initialize. For that, we have to initialize. It will take some time to initialize. So it is now in standby. So we'll choose 2 theta theta here, and the control will be move. So here 10 is in the initial position. So we'll choose 50, and then we'll execute it, and you can see how it is moving. So now the 2 theta angle is 50. Now we are moving further to 90. So we are doing it manually. But when it scans, it will be moved as per the scanning rate we have already chosen in the condition. So the 2 theta is in 90 degree now. So again we are reversing it. Then we choose 10. So this is for the XRD. So if you have any question, then please ask. Otherwise, I'll request Jyotireka Mollik. So she is research scholar here at IIT Patna. Is there any question? Sir?
Yes, I think
Sir, then
we can proceed because, yeah, so these teachers, maybe at the moment they are not having any questions.
okay, sir.
So Jyoti is going to demonstrate retwelt, or like what kind of a thing is she planning to do?
Yes, sir, for the XRD data analysis.
Okay.
Jyotireka Mollik? Jyotireka?
Yes, sir.
So
she can share screen,
are you ready?
Right?
Yes, sir, I am ready.
Okay, then I'm switching off the video now. Thank you.
Okay, sir.
Thank you.
Is the slides are visible?
Yes, it is clearly visible.
Okay, sir. Thank you, sir. Good afternoon, everyone. I am going to discuss about the readable refinement of XRD patterns. It is a very useful technique which is used to analyze the Pardo diffraction data in terms of profile fitting, strain calculation, structure distortion, and structure refinement. It is
Jyotireka, you have to ensure that there's nobody else with a device on in like with audio on,
yes, sir. Yes, sir. Now
right? Joining to the Teams. Yeah.
okay, sir.
Maybe they can look at the same screen or yeah. Thank you.
Okay, sir. Okay, sir. This Rietveld refinement generally developed by Dr. Hugo M. Rietveld. He this refinement is generally described means the profile fitting technique or data fitting technique of XRD data. Means this refinement cannot generate any readable refinement data from no data. So for that you have some XRD data before the fitting. Means after the X-ray diffraction you get some data, and from that data you get we got the intensity and Bragg position. By using that we can form a DAT file. By using that you can do the readable refinement. And this readable refinement generally analyze the diffraction patterns of diffraction pattern by using full profile fitting. Means this fitting can fit all the peaks by using some function. Rather than this, it can describe the phase analysis, refine the lattice parameter, atomic position, occupancy, etc. And this readable refinement can be done by using foolproof suite software. For this foolproof suite software, you must have two files. One is PCR file, another one is DAT file. Here now I am going to discuss how to make the DAT file from the XRD data. In the XRD data, you can see there is this x in the x-axis there is intense Bragg position, and y-axis this is intensity. First you have to select that, copy this intensity and go to the Excel sheet, put here the initial Bragg position, where in this case the initial Bragg position is 20 and the step size is 0.02 and the final Bragg position is 80. And in the B axis you have to paste the intensity and save this. In the format text tab delimited form. Okay, by opening this is in the form of text document. First open this in by using Notepad and save this text document in the form of dat file, means btu.dat. Hence you got the dat file of your data. Now I am described how to make the PCR file. To make the PCR file of your data, select this foolproof suite software. Then go to the EDPCR. After that, you got this icon, and in this icon, you select this new data form and go to this journal. In general, you have to give the name of your sample. Here I have insert the barium titanium oxide, as this is a refinement. So in the calculation section, you have to click on the refinement / calculation of a power diffraction profile. Then click on OK button. Then go to the patterns. Click on this data file or peak shape. In data file or peak shape, you have to input here that data file that you have found previously. Browse this and go to the file, upload this here. Here, this data file is in the format of 2 theta initial, then the step, then 2 theta final. So you have to keep tick on this icon. After that, you have to go the refinement or simulation section. In that section, you see that there is a X-ray, another one is pattern calculation X-ray. This X-ray generally, you have, if you want to refine the data, you select this X-ray. If you want to simulate the data, you have choose this pattern calculation. But here we want to refine the data, so that we take on this X-ray. Then this is the wavelength. This is the wavelength of the target material that is used in the XRD. In our case, the target is made up of copper, so you have chosen the copper, and correspondingly the wavelength is coming here. Then go to the pattern calculation peak shape. For the peak shape, you have to for peak shape you have to choose the pseudo Vogt, because the peak, the XRD peak that we have got from the XRD data is the combination of Gaussian and Lorentzian function, and this pseudo Vogt denotes the combination of Lorentzian Gaussian peak. That's why here you have choose the pseudo Vogt peak, and here the scattering value, which is in the form of 2 theta. Then in this region, you put the range, that is theta minimum, where in this case the theta minimum is 20 degree and theta maximum is 80 degree. Here the step size is 0.02. Then click on the OK button. After that, go to the background type. Here there are so many options. If your background XRD pattern background is linear, then you can choose 6 coefficient polynomial or 12 coefficient polynomial. If your background type is amorphous type or it is a slopy type, then in that case you can use the linear interpolation between a set background points with definable heights. After that, you can go to the phase. At first, you have to know some basic thing about the sample, means what is its phase, and also its in what range its lattice parameter belongs to. So in this case, the sample has phase is tetragonal, so I input here tetragonal, and in the calculation section there are so many options. Here magnetic phase with magnetic moment, which are used in neutron diffraction method. But in this particular case, we want to refine the atomic position lattice parameter. That's why you have chosen structural model, that is Rydberg method. Then go to this contribution to patterns. This contribution patterns, you have to select this X-ray, and in this peak shape you have to select this pseudo Vogt. Then click on OK. After that, you have to choose the symmetry operation. In symmetry operation, you have to input this space group, means what space group your sample is belongs to. That this is the just a guess, means P for here the sample maybe belongs to P for mm, and between each parameter you have to give a separation. Then click on OK. After that, your file is ready to refine. After all those things, you have to click this icon, which will save your data. and this data will be saved in the same dat file where your dat file is. This is the refinement information. The first one denotes the cycles of refinement, means in each refinement how many times of cycle you want to refine it, you have to include here. And in the refinement section there is some sequence, means first you have to refine the scale parameter, then you have go scale parameter which is in this profile section, then you have to go to refine this background. After that you have to go to the lattice parameters which is present in this profile section, and after that you have to refine this atoms information. So in the profile section, you first click on this scale parameter and click on this OK button and go to this and click on this icon so that the scale parameter will be refined. Then go to the background. In background section, you at first you have selected 6 coefficient polynomial. That's why there are 6 parameters is coming, and you will refine one by one. After that you can take the combination of them and refine it. Then go to the profile and refine this lattice parameter alpha beta gamma, then FWHM which is depend upon the UVW, and always remember that this V value must be negative. Then go to the shape parameter, that is eta and x, which is related to the pseudo-Vega shape of your XRD pattern. Then go to the atoms where I have selected 4 atoms. Generally here barium, titanium, oxygen, oxygen 1, oxygen 2. Here BaTiO3, and the 6 oxygen atoms are placed at the 6 faces of a cube, and 4 oxygen are one plane and 2 oxygens are in another plane. Here the oxygen ratio is 2:4, that is 1:2. That's why I have here written oxygen 1 and oxygen 2. Then you can put in this occupancy of the barium place is 1 and titanium place is 1, then oxygen 1 is place 1, and for oxygen 2 you can write the oxygen occupancy as 2. Then this B factor is belongs to thermal factor, means it denotes the vibration, thermal vibration of an atom. If the your atom is at low temperature, then the vibration takes place equilibriumly in all directions. There you can choose isotropic. If the thermal vibration is at higher temperature, and if your atom is at higher temperature, so the vibration takes place randomly. In that case you can choose anisotropic in the thermal factor. Then after that you can refine XYZ, and by clicking this file you can upload the PCR file and click on that icon. You can refine your data. Now I am going to run a data. Here I am going to the upload this PCR file, then run full program. You can get this fitting. Here you see that chi-square, this chi-square, if this chi-square value is below 3, then you can see that you can conclude that your theoretical data and your experiment data are in good fit, and this chi-square it generally depends upon the R factors, which are the mathematical, which are some mathematical model and these are RP, R omega P, R expected, but the chi-square is depend upon the ratio between the R omega P and R expected. After this refinement, you see that first you have PCR file and dat file. Here you get some another file in the out file. you can get the refined lattice parameter, strain, XY position, occupancy of your sample. And by using this Vesta file and upload it, Vesta file and CIF file, I uploading it in the Vesta software, you can get the 3D representation of your 3D representation of crystal structure of your sample. This is all about the Ripple refinement. If there is any question, you can ask me. Hello, sir.
Yeah, let us see if there are any questions. So are there any questions? So let me ask a question to the FDP participants. So can they now tell us what is Rietveld refinement? Somebody would like to address this? The question is for the participants. So Jyotirekha, it was an excellent explanation. Yeah, yes, somebody is unmuted. Please go ahead. Okay, it looks like Jyotirika, your colleague or someone in the lab itself spoke something. Yeah. Okay, fine. So like Rietveld refinement is one of the very important techniques used by people who work with materials in order to establish the quality of materials which are made. So in particular, like if you use it suitably, right, for say XRD data, you can obtain the residual strain within the sample, like an important quantity which is otherwise very difficult to estimate. The same technique is also used by people who use neutron diffraction techniques, and a lot of crucial magnetic information could be extracted. So it is a very strong method, right, or a strong technique. So fine, so we will kind of close this session now. Thank you, Jyoti Rekha. Thank you, Bidyendu.
Thank you, sir.
Yeah, thank you so much.